All right, everyone, we're back. So now we are pretty familiar with the planets of the solar system. We've talked about the terrestrial and Jovian planets. So I think it is time to talk about exactly how we think planets formed. But planetary formation is really intimately tied with the formation of their host star. So, to understand how planets form, we need to first at least have a cursory understanding of how stars form. Okay. Star formation and the subsequent formation of planets can be broken down really into five stages. And that is like the dark cloud or the nebula stage, kind of right over here. Then that star goes through kind of a gravitational contraction or gravitational collapse. You get a protostar and a protoplanetary disk. And then the whole system, like the disk kind of goes through what we call a clearing. So let's just start from stage one, right? The dark cloud or the nebula phase. So right here on your screen, this is an image of the Orion Molecular Cloud Complex. We have the Orion Nebula right here. It's a small part of it. This is what we would call a star-forming region. Stars need huge clouds of gas and dust to form, right? This is the fuel for star formation. And right here, this is a whole bunch of gas and dust. Just having the gas and dust is not enough, though. These clouds need to be pretty cold, about 10 Kelvin, which is about a negative 440 degrees Fahrenheit. The clouds are also pretty diffuse if we're just talking about kind of like our daily, in terms of like our daily lives, right? The typical density is about maybe 10 to the 4 molecules per cubic centimeter. Earth's atmosphere, just for reference, is about 10 to the 19 molecules per cubic centimeter, so much more diffuse than the atmosphere of the Earth. These clouds are also dark, right? They block up to 10 magnitudes of starlight at the center. Um, Out towards the edges, more starlight gets through, the edges get a little more heated, but at the center, it really, not a lot of starlight gets through. So this blockage, which we call extinction, has a consequence. So light from stars outside the cloud doesn't get into the center. The light can't transfer energy to the center of the cloud, right? That center of the cloud can't heat up. So this allows what is normally diffuse gas, it allows it to form ices, which make the cloud even darker and colder. So temperature and mass are very important because these are the two things that will lead to the second phase, which is gravitational contraction or gravitational collapse. So we have this cloud out in space and it is slowly rotating. It's not just really sitting there still, it's got a little twist to it. When it gets massive enough or cold enough, this cloud will begin to collapse under its own weight. This is called a Jeans instability. You don't have to know that for anything. It's just what it's called. So we have this slowly rotating mass of gas start to collapse in on itself. It contracts, right? It gets smaller. So what does this imply? So this implies that the rotation of this gas cloud will speed up, and this has to do with the angular momentum of the system. So if you don't remember from, high school physics, angular momentum is a property of rotating bodies that resists tilting. Um, it's also called a conserved quantity. This means that the angular momentum of an object shouldn't change in an isolated system as that system evolves over time. So angular momentum depends on the mass of the object, its rotation speed, and its shape. So kind of the classic example of this is an ice skater spinning in a circle. When their arms are away from their bodies, they slow down. When they pull them in, they go faster. I'm going to see if I can actually play this video for you. There we go. The arms out. Pull them in. It's going faster and faster. Okay, so see, this happens with the gas clouds, right? The contraction process, it compresses the gas and dust into a rapidly rotating central object. So if all the mass of a cloud collapsed like into a sphere, right, like into this protostar, it would spin faster than the speed of light. So that would be very unstable. So it doesn't do that. Instead, most, I mean, like 99% of the mass of the cloud goes into the protostar, and the rest forms a thin protoplanetary disk. So we kind of have a protostar and a protoplanetary disk kind of forming at roughly the same time. So right here we have our gas cloud collapsing down into the protostar. And then here we kind of have our protoplanetary disk and protostar phase. So when the protostar gains enough mass to start nuclear fusion in its core, it becomes a star, right? That's what separates a star from a protostar, that nuclear fusion in the core. The rest of the material is kind of spun out into a thin disk. This conserves angular momentum, which is very important. It's not solid. It's not like a frisbee, right? Or you that just a solid disk. It's the leftover gas and dust from that molecular cloud. So we've actually captured images of protoplanetary disks. The first one ever imaged, I think, is right here on your screen. This is HH30. It was imaged by Hubble in 1995. But it was also imaged just recently by the James Webb Space Telescope, and that's over here. This is an infrared image where you can definitely see the resemblance. This was released about a month ago. So on the left, we have Hubble in optical wavelengths. The left is JWST in the infrared. The JWST image is actually labeled with features, um, the features of this protoplanetary disk. So you really can't see the disk. It is behind this dark lane right here, but it is there. You can also see jets coming out of basically the top and the bottom, which we will talk about a little bit later, as well as some other types of outflows. So this is a protoplanetary disk. It is, I guess you could think of it as like a solar system in the making. Another very cool image of a protoplanetary disk is HL Tau. So this is in the radio. So this is nowhere near like what we would see with our eyes, but it's pretty much what we would expect to see. Um, it's got kind of the bright central, probably a star at this point, and dark lanes kind of in the disk where we expect planets to be forming or maybe have already formed. So we expect protoplanetary disks to look a certain way. So this is a little bit of a complicated diagram, but I really want you to pay attention to its shape and where the cold part of the disk is. So we expect these disks to be mostly flat, but with a little flare, right, out towards the edge, right? So it's pretty flat, but it flares out like this. Um, we expect it to also be basically opaque at the center, right? So remember we talked about the molecular clouds and how there's this extinction, right? Starlight can only penetrate so far into it. And that's the same thing here. If we have a star or a protostar, it will shine light, but it will only get so far into its own protoplanetary disk. And so we have kind of this region here that ends up being pretty cold. And that's going to be important for what types of planets will form out there. Because we expect this to be the location of planet formation, and we basically think there are two mechanisms behind this. One is coagulation, and one is called gravitational instability. So let's think about what is happening in this protoplanetary disk. Um, at this point, we have maybe a central star, and its radiation is heating up the inner disk and the edges of the disk. But because of extinction, the radiation is not getting through the entire disk. Remember, starlight only penetrates so far, and this leaves a cold, dark center of the disk. So the region beyond which water can actually freeze out and form ice, that is called the snow line. On this image, they call it the frost line, but that's the same. That's the same thing. So coagulation is when larger bodies form by smaller bodies kind of colliding and sticking together. So between the star and the snow line or the frost line, we think that planets must form through this method, through coagulation. Otherwise, it's way too hot. Planets can form beyond the snow line in this way as well, but beyond the snow line, planets can also form by a process known as gravitational instability. So this is actually very similar to how the star formed to begin with, right? In this region, large enough columns of molecular gas can form and collapse under their own weight. So this is likely the formation mechanism for the giant planets of our solar system. So during this process of planet formation, we will enter a fifth phase. It's the clearing phase. So during planet formation, multiple processes are occurring in the disk that affects gas, dust, and planetesimals, right? These kind of smaller rocky bodies flying around. So gravity causes accretion or inflow of material to the star. So material can fall in, like the sun has a major gravitational pull, material will fall in around the sun, and that material can either fall into the star, into the sun, or it can be flung out. If it's flung out, this will look like a jet, like those we saw in HH30. Stellar wind, though, can also act to blow material outward. So the stellar wind coming from the sun can blow material outward. So this could result in a boundary, or this does result in a boundary called the heliopause. You can kind of think of that as really roughly kind of a boundary to the solar system. Material can also be flung around by the outer gas planets, either into the inner solar system or outward. So we have gas giants perhaps forming out here where it's nice and cold, and it can either fling material into the solar system or into the inner solar system, or it can kind of fling material out, kind of like up and out. So the material that's flung out by these planets, we think formed the Oort cloud, which is something we will talk about a little bit more in a later lecture. So this clearing process was probably a really violent time in the history of the solar system. Um, we see today like really heavily cratered inner planets, right? Mercury, the moon, all have like a lot of craters on them. This is evidence of this time when smaller objects are being flung into the inner solar system. So we can look for evidence that our solar system formed in this way. So one of the big indicators is a gap in conditions, we can call it. So we have the inner planets, a population of rocky terrestrial planets, and a population of gas and ice giants, kind of in the outer planetary part of the solar system. So around the asteroid belt here, probably corresponds to the snow line, right? And giant planets in the outer solar system, um, probably formed by the gravitational collapse. So the snow line is actually thought to be somewhere in the middle of the asteroid belt. And we do see different distributions of asteroids within the belt. So the inner asteroid belt is mostly made up of rocky asteroids, while the outer asteroid belt is made of what are called carbonaceous asteroids, which tend to be made in cooler conditions. Also, the solar system is roughly planar, right? It's on a plane, like we would expect if the solar system was formed out of a protoplanetary disk. So this model seems to fit our solar system very well. And the better we understand our system, the better able we are to compare it to other star systems and exoplanetary systems. That'll be the real test of whether or not the details of our model are correct for planetary systems broadly.